collection of real numbers. Majority of the work that we have done, or basically all the work that we have done up till now, has been done in the collection of real numbers. Anything like -1 or say 2.795 or say 11 upon 27 or say 654, all these types of numbers including integers, rationals, irrationals, natural numbers, all of them are real numbers. But then we encountered that there are certain problems which cannot be solved with the help of real numbers in mathematics. There were certain equations which were not solvable even when so many real numbers were available. None of the real number was able to satisfy that equation. That means all equations were not solvable in the collection of all reals. Encountering such a problem, Euler helped us to get a solution of that. He introduced, or basically he incorporated, some imaginary numbers in basically the real numbers, or basically I should say that some imaginary numbers were invented and introduced in order to combat such problems. What were these imaginary numbers? Nothing but just adjoin every real number with iota and you get your imaginary numbers. Right? Because if small x is what stands for the representation of real numbers, iota times small x is the representation of imaginary numbers. So every imaginary number is made up with iota and a real number. So that is what imaginary numbers basically look like, but still there was a certain problem. Like I told you, there were many equations which were now solved with the help of imaginary numbers. But still there were some problems, some equations which were not solvable even with these. For example, I told you an equation like this. This equation is not solvable in the collection of all reals. In fact, none of the imaginary numbers are also able to satisfy this. That is why this basically intrigued all the scientists and mathematicians to basically increase the set even more. Having increased from the real numbers to imaginary numbers did not suffice the solving of all the problems. That means more numbers were required and that led to the construction of complex numbers. Complex numbers were nothing but the sum of real and imaginary numbers, and so in the set of imaginary numbers, I should say, some more complex advanced numbers were adjoined that were basically something like, -1 plus 2 iota, or 7 minus 9 iota, or I should say 11 by 5 plus 3.5 iota, or I should say 68 plus 71 iota. So these type of numbers were adjoined and the set was made even larger. This set was known as the set of complex numbers. How do you think this equation attains its solution in the set of complex numbers? Well, over here, if this is the equation that you have, in the next step I can write x plus 1 is equal to under root minus 9. Now, square root of negative of a positive real is an imaginary quantity. This is an imaginary quantity. That means this will be equal to under root 9 into under root minus 1. By the note that we had done in the previous class, because among 9 and minus 1, 9 is non-negative, I can break this root and write it in the form of this. Now, root 9 is plus minus 3 and root over minus 1 is iota. That means what is your x? X happens to be minus 1 plus minus 3 iota, which implies x is equal to minus 1 plus 3 iota and x is equals to minus 1 minus 3 iota. That means the solution of this equation are these two complex numbers. They are not real numbers, they are not imaginary numbers, but they are sum of real and imaginary numbers. They are complex numbers. These were the equations which could not be solved by real or imaginary numbers, and for them or for equations like these, the set was increased even more to let complex numbers come in, and then these complex numbers basically helped this particular equation to be solvable. Okay? That was what was the need of complex numbers, that was what was the basic evolution, how the complex numbers came into picture. Up till now, complex numbers happen to be the largest set of numbers. There is no equation which cannot be solved with the help of complex numbers. And so, till now, this set has not been increased further, because all the problems up till now are being solved with the help of complex numbers, right? If there exists some problem in future, then maybe we may extend this particular set as well by adjoining some more elements inside this set of complex numbers. Till now, this happens to be the largest set which we are going to study in detail now on. So, once we have understood all of this, we formally led to the definition of complex numbers, and we realized that every complex number is denoted by small z, and it is nothing but the sum of real and imaginary numbers. You just take a real number, add to it an imaginary number, and you get your complex numbers. That's how complex numbers are. Any number which looks like this is a complex number. Now, one thing which you should very, very nicely realize is that a complex number is made up with a real number and an imaginary number, but an imaginary number in itself is made up with an iota and another real number. That means a complex number is made up with two real numbers. One real number, another real number and an iota. A complex number is made up with two real numbers and an iota. That means if I give you two real numbers and an iota, can you form the complex number? Well, suppose I give you 2 and 3, iota you know you already are going to have. If I give you just two real numbers, in your mind you know there is iota already present. Can you from this make a unique complex number? We discovered that no. I can make 2 sit like this and 3 adjoin with iota to give me the complex number, say z1, or I can say 3 plus 2 iota to give me the complex number z2. That means with the help of two real numbers, I cannot construct a unique complex number. That means not just a complex number is made up with two real numbers, because over here I can say z1 is made up with 2 and 3, z2 is also made up with 2 and 3, right? So, made up with 2 and 3, z1 and z2 are made up with 2 and 3. That means when I say that I am giving you two real numbers, I cannot come up with a unique complex number. So, what is it which is going to allow me to come up with a unique complex number made up with 2 and 3? The point is, where is 2 sitting and where is 3 sitting in the complex number? If 2 is sitting alone and 3 is adjoined with iota, or 3 is sitting alone and 2 is adjoined with iota. If 2 is sitting alone, 2 is the real number which will be contributing to construct the real part of this complex number z1. And like 3 is sitting adjoined with iota, 3 is basically making up the imaginary part of this complex number z1. Over here 3 is sitting alone. So, 3 is basically contributing to the real part of the complex number z2, and because 2 is adjoined with iota, 2 is contributing to the imaginary part of the complex number z2. That means a complex number is not just made with two real numbers. The two real numbers possess their individual powers. If I say 2 and 3 are the two real numbers by which a complex number is made, the next question of yours should be, 2 possesses which power? Does 2 possess the power to be the real part of the complex number, or does 2 possesses the power of being the imaginary part of the complex number? Similarly, what are the powers which 3 has? Suppose I tell you that I give you two real numbers 2 and 3 such that the real number 2 possesses the power of being the real part of the complex number, and 3 possesses the power of being the imaginary part of the complex number. The moment I tell you this, you are in a position to come up with a unique complex number. Now the complex number which you are going to make will not just be made with 2 and 3, but because you know 2 possesses the qualification, in short, 2 possesses the power of being the real part of the complex number, and 3 basically is qualified to become the imaginary part of the complex number. That means this complex number can never be made once you know all of this. Because 2 does not possess the power of being the imaginary part, so how can I keep 2 here? 3 does not possess the power of being the real part, so how can I keep 3 over here? That means the only complex number which you are going to make will be this. And so, in short, if I just summarize what I wish to say is that any complex number is made up with 2 real numbers, wherein those 2 real numbers are not just any randomly selected real numbers, but in fact, the moment those 2 real numbers are selected, each real number among these 2 real numbers possesses their own power. One real number possesses the power of being the real part of the complex number, another real number possesses the power of being the imaginary part of the complex number. The real number which possesses the power to be the real part sits alone in the complex number, and the real number which possesses the power of being the imaginary part adjoins with iota and then sit in the complex number. When these two get added, you get your complex number. And so, if you know the real part and the imaginary part of a complex number, you can construct your complex number. Because when I am saying that you know the real part and imaginary part of the complex number, that means you know 2 real numbers, and with those 2 real numbers you also know which real number is the real part and which real number is the imaginary part. The moment you know this, you are in a position to form your complex number. Okay? That means a complex number is not just equals to a plus ib, where a happens to be the real part of the complex number and b happens to be the imaginary part of the complex number. But in fact, conversely, if I am given 2 real numbers and I know which one contributes to the real part and which one contributes to the imaginary part, I can come up with a complex number, right? The next definitions which are going to come in the league are purely real and purely imaginary complex numbers. Right? What is the meaning of purely real complex number? Let's see. Let z equals a plus ib be any complex number. Then, if a is equal to 0, the real number which a is 0. That is, what is a? Real part of the complex number z is 0. Then, complex number is called purely imaginary. Why? Because if small a is equal to 0, then z happens to be 0 plus iota b, which is just iota b. And I know these are basically the representations of imaginary numbers. So, if the real part of the complex number z happens to be 0, the real number which sits alone in the complex number is 0, then z is just equal to an imaginary number, iota times b, and therefore such complex numbers are called purely imaginary complex numbers. That means any imaginary number basically are those complex numbers with real part 0. Imaginary numbers are those complex numbers with real part 0. That is why every imaginary number is a complex number known as purely imaginary complex number. And so we understood what is purely imaginary complex number. And if you have b, if b is equal to 0 in z equals a plus ib, this implies that z is equal to a plus iota times 0. This implies that z is just equal to a. Okay? That means if b is equal to 0, that means the real number which is adjoining with iota, the imaginary part of the complex number is 0. That is, when the imaginary part of the complex number given by b is 0, then it's called a purely real complex number. Because then z is just equal to a real number, there is no imaginary part. Imaginary part vanishes, it becomes 0, and therefore z just turns out to be a real number. And that is why such complex numbers with imaginary part 0 are known as purely real complex numbers. That is why, because every real number can be written as that real number plus iota times 0, therefore every real number is a complex number with imaginary part 0. That means every real number is a purely real complex number. This is another reason why every imaginary number is a complex number. In fact, it is a purely imaginary complex number, and every real number is also a complex number. They are purely real complex numbers. Okay? So once these definitions are clear to us, it's now time to move on to the operations with complex numbers. Why? Because just like when we studied real numbers, we studied several of operations to bind them together to form new real numbers. In a similar fashion, now that we are studying new types of numbers, which are the complex numbers, which are nothing but the addition of real and imaginary numbers, we have been introduced to this new space, new set of numbers. So definitely it is a curiosity and a duty as well to be able to learning all the operations which are able to bind these complex numbers to create new complex numbers. So let's see the operations which are valid in the collection of all reals. The same operations are valid in the collection of all complex numbers or not, and if they are valid, how are they defined? Okay? So let us very first thing talk about equality of complex numbers. Right? Let's talk about this. I am saying that let z1 equals a1 plus iota times b1 and z2 is a2 plus iota times b2 be any two complex numbers. These are just two complex numbers given to you. When can you say that two complex numbers are equal? When can you say a1 plus iota times b1 is equal to a2 plus iota times b2? When can you say this? Well, the general intuition says that the real number which are sitting alone in both the complex numbers should be equal, and the real numbers which are adjoined with iota in both the complex numbers should be equal, right? If a1 is equal to a2 and b1 is equal to b2, then I say that two complex numbers a1 plus iota b1 is equal to a2 plus iota b2 are equal. Let both roots of this particular quadratic equation be greater than 3. That's the main major trigger word. Both roots of this quadratic equation are greater than 3. Now the thing which is right now popping inside my brain is that I have learned something about what are the conditions when two roots of a quadratic equation are greater than k, isn't it? Let's polish that concept and then get back to the question in order to tackle it. Well, if ax square plus bx plus c equals 0, where a is non-zero, has two roots alpha and beta such that alpha and beta both are greater than k. K is any number on the real line. So, if alpha and beta are the two roots of this quadratic equation such that both are greater than k, then the condition are, what are the conditions? Well, there are three conditions which should be satisfied for this quadratic equation to have both its roots to be greater than k. Fine. What are the conditions? First thing is that the discriminant should be non-negative. We know that. Secondly, now why discriminant should be non-negative? Because either both the roots are real or both real and unequal, or both the roots are real and equal. But if discriminant is less than 0, that means there are no two real roots, and that is not the case which is happening over here. So discriminant can either be positive or discriminant can be equal to 0 as well. Next condition is a into f of k should be positive, where a standing here is the coefficient of x square, which is non-zero, and f of k is the value of fx at k, where I am saying my fx is nothing but the quadratic polynomial associated with this quadratic equation. Fine. And the third condition was what? It was that the abscissa of the vertex of the parabola being represented by this particular quadratic polynomial should be what? Greater than k. The abscissa of the vertex is this only, right? Minus b upon 2a comma minus d upon 4a are the coordinates of the vertex, out of which the x coordinate is this. This should be strictly greater than k. Only and only when these three conditions simultaneously are getting satisfied can I say that the two roots alpha and beta of this quadratic equation are greater than k. Fine. So these are the three conditions which should be satisfied regarding this quadratic equation. In our question, we are given this type of a quadratic equation. Let's copy that down. It is x square minus 6ax plus 2 minus 2a plus 9a square. This is my fx, and I have considered fx equals 0. Fine. This is my quadratic equation. What is my a? A is 1 over here. If I compare it to the general quadratic equation ax square plus bx plus c, this is 1x square. Fine. B is what? Minus 6a. And what is my c? That's the constant term. 2 minus 2a plus 9a square. Fine. If this quadratic equation has two roots strictly greater than 3, so let the two roots be alpha and beta. So either these two roots are equal to each other, right, or they are unequal to each other. In any case, one thing is evident, because a is strictly positive. A is strictly positive, the parabola which will be represented by this particular polynomial will be opening upwards, right? You will have your parabola opening upwards. So if A is positive and discriminant is also positive, then what is going to happen? The parabola is basically going to open upwards. Fine, intersecting the x-axis at two distinct points which happen to be your roots alpha and beta. Or you can have a scenario in which A is positive but discriminant is 0. Again the parabola opens upwards, but this time alpha is equal to beta, right? This is nothing but ax square plus bx plus c, and this is also ax square plus bx plus c, where a is 1, b is minus 6a, and c is your 2 minus 2a plus 9a square. If both the roots of this particular quadratic polynomial which is given to me fx are greater than 3, in that case I know what are the three conditions which govern this particular concept. Well, if both the roots are strictly greater than 3, definitely 3 is over here, they both are greater than 3, or it won't be such a polynomial because of such a graph, because over here alpha is coming out to be less than 3. Alpha is coming out on the negative real line. So instead of this, you can have, if discriminant is strictly positive, you are going to have something like this type of a polynomial. So this will be your alpha, this will be your beta, somewhere here is your 3 lying. This is ax square plus bx plus c when a is positive and d is also positive. So if such is the case, definitely the first condition which should be satisfied by my quadratic polynomial is that its discriminant should be non-negative. So that's the first condition, that discriminant should be non-negative, which means b square minus 4ac should be non-negative. That's the formula of discriminant. Now b square, what is b? b is minus 6a, minus 6a whole square, that means 36a square, minus 4 into a into c. a is 1 and c is 2 minus 2a plus 9a square. This has to be non-negative, which implies 36a square minus 8 plus 8a minus 36a square, isn't it? This is minus 8, then you have plus 8a minus 36a square. This 36a square, this 36a square, they get cancelled. You are left with 8a minus 8 is non-negative, which implies 8. A minus 1 is non-negative. So for 8 into something to be non-negative, definitely that something also has to be non-negative, right? Because 8 is already positive. So 8 into anything negative will give you negative, but the answer is non-negative. So 8 into something is giving you non-negative means this thing has to be non-negative, which implies a minus 1 has to be non-negative, or a has to be greater than or equal to 1. So the first condition which is going to permit this particular quadratic equation to have both its roots to be greater than 3 is that first of all a has to be greater than or equal to 1. And there is something more which should be holding. What is that something more which should be holding? That will be given by the second very condition, which is a into f of k has to be greater than 0. Fine. So, if both the roots are greater than 3, definitely a into f of k has to be, it will be greater than 0. What is a? A was 1. A was 1. So, f of k, where k is 3, has to be greater than 0. What is f of 3? So, if f of x is x square minus 6ax plus 2 minus 2a plus 9a square, therefore, f of 3 will be 9 minus 18a plus 2 minus 2a plus 9a square, right? This leaves you with 9a square. Then you have minus 18 minus 2, which is minus 20a plus 11, right? If you try to break it up, what are you going to get? This is how you're going to break the middle term as minus 9a minus 11a happens to be minus 20a, and when you take the product you get 99. So, over here take out 9a common, you're left with a minus 1 minus 11 a minus 1. This gives you what? 9a minus 11 and a minus 1. So, f of 3 is coming out to be broken up into two distinct factors, 9a minus 11 and a minus 1. If you want f of 3 to be positive, if f of 3 is positive, that means this is positive, right? Product of these two things is positive. How do we basically try to get the range of a for which this product is going to be positive? Well, we go and plot the number line. Infinity, this is minus infinity. What are the two important points which are being denoted over here? A equals 1 and a equals 11 by 9, which is greater than 1. Fine? So, this is what you have. Now, if you plug in the values of a which are less than 1, values which are less than 1, that is going to give you what? What is that going to give you? If you plug in the values less than 1, this factor will be negative. Plug in the values less than 1, they will automatically be less than 11 by 9. So, this factor is going to give you negative answer. Negative into negative makes it positive. If you plug in values which are greater than 1 but less than 11 by 9 over here, if a belongs to such a range, what is going to happen is plugging in a value which is greater than 1 is going to make this factor deliver you with a positive answer, but this is going to deliver still a negative answer. So, positive into negative is negative, and then if you take any value greater than 11 by 9, this is positive, so the product is positive, right? And therefore, we have obtained for which a's on the real line is this factor coming out to be positive. So, for a is equal to, or a is belonging to the range of minus infinity to open 1 and a is belonging to the range of 11 by 9 comma infinity. Fine. So, from the first condition of discriminant, I have obtained that if I have a quadratic equation whose both roots are strictly greater than 3, that means definitely its discriminant will be non-negative. That means definitely a has to be greater than or equal to 1. If I have an equation, quadratic equation whose both roots are strictly greater than 3, definitely a into f of k would be positive. For a into f of k to be positive, definitely a will be belonging to this range. So, I have got a is greater than or equal to 1. I have also got a is belonging to such a range. There is just one more condition left. Let's see what that is. There are three conditions which get satisfied if there is a quadratic equation with both its roots to be strictly greater than a constant k. The third condition is that minus b upon 2a would be greater than k. Now, what is b? B is minus 6a, so minus b will be 6a upon 2 into a is your 1, so you are just left with 2, strictly greater than k, which is your 3, which implies 6a is greater than 6, which implies a is greater than 1. So, I have got 3 restrictions on a from the 3 conditions which are true for this quadratic equation. Because this quadratic equation which is given to me in the question has both its roots strictly greater than 3. That means this is also true, this is also true, and this is also true. Fine? And that is why to find out the range in which a lies, why are we doing that? Because I want such an a which satisfies this also, and this also. That means I have to find a which lies in the common region of all 3 these regions. What is that region? Let's find out. So I have, if I talk about the number line, this is my 1 and this is suppose 11 by 9. Fine? First condition says a has to be greater than or equal to 1. So it can be either 1 or greater than 1. 1 is included, either 1 or greater than 1. This is the range of a's which is coming from the first condition. Second condition says a belongs to minus infinity, comma 1, 1 open, 11 by 9, comma infinity, where 11 by 9 is open. So, minus infinity to 1. 1 is excluded, and 11 by 9 again excluded to infinity. So this range and this range is the range given by the next a. Fine? The third a's range we have is a is strictly greater than 1. That means what? I can alternatively write it as a belongs to 1 comma infinity. It's strictly greater than 1. So this is what I have from the third very answer of A. So what is the common region? You can definitely see that this region is the common region. That means those A's for which discriminant will be non-negative, A into f of k will be positive, minus b upon 2a will be greater than k. Which A's are there? The A's are these A's. Therefore, the appropriate range of the unknown A given to me in the question is what? 11 by 9 open, okay, 11 by 9 open, comma, infinity, because it's not included over here. Fine? And that is what is my A for which, these are my A's for which this particular quadratic equation is going to have both its roots greater than the constant 3. Let's see which option gives me that particular answer. 11 comma infinity, no, that's wrong. 11 by 9 comma infinity, yes, that's correct. Minus infinity comma 1 union 11 by 9 comma infinity, no, that is just going to satisfy partially all the 3 conditions of this particular quadratic equation to have both its roots greater than 3. Fine? This is wrong, even this is wrong. Modulus of z and modulus of w is exactly the same. Here, if it is equal to k and alpha is given by z minus w bar upon k square plus z w bar, then real part of alpha is what? Now see, the moment I show that alpha plus alpha bar is 0, this itself means that real part of alpha is 0. Right? Keeping this in mind, if I consider alpha bar, if alpha is this, alpha bar is z bar minus w bar bar, which is w, upon k square bar, which is k square, plus z bar w bar bar, which is again w. Right? Now it is given to you that mod z equals mod w equals k. Mod z equals mod w equals k. This means mod z square equals mod w square equals k square. This is zz bar, this is ww bar equals k square. So z bar is k square by z and W is k square by W bar. So here if you incorporate those values, Z bar is k square by Z, W is k square by W bar whole upon k square plus Z bar into W. So Z bar is k square by Z and W is k square by W bar. Simplify this, what do you get is alpha bar is k square common W bar minus Z whole upon, again you can see k square ZW bar plus k square into k square. So k square can come out common and this is what you have. This gets cancelled, you are left with W bar minus Z upon ZW bar plus k square, which is nothing but minus alpha. Once you get this, you have got alpha plus alpha bar is 0, which means real part of alpha is 0, and the question was what is the real part of alpha, and so your answer is that it is 0. Clear? Moving on to the next question, we have if Z1 or Z and Z2 are Z1 itself are non-zero complex numbers such that mod Z1 equals mod Z2 equals mod of Z1 plus Z2, then Z1 by Z2 can be what all values among these? See, now over here you need to very clearly understand that mod of Z1 by Z2 is actually equal to mod Z1 upon mod Z2. So if you are given this means mod of Z1 by Z2 is actually 1. And you are also given this, that means mod of Z1 plus Z2 upon mod Z2 is 1. This can be written as whole mod of Z1 by Z2 plus Z2 by Z2, that is 1. So what do you mean by this equals this, which is equal to 1? That means I can write this as Z1 by Z2 minus 0 plus 0 iota equals Z1 by Z2 minus 1 plus 0 iota, and this is equal to 1. This means Z1 by Z2's distance from this complex number is same as its distance from this complex number, which is 1. That means Z1 by Z2 lies on the perpendicular bisector of the line segment joining 0 plus 0 iota and minus 1 plus 0 iota. So if that is the situation, it's pretty simple to understand. This is 0 plus 0 iota or 0 comma 0 ordered pair. This is say minus 1 plus 0 iota, then the perpendicular bisector is this. What is this point? Minus half comma 0. Z1 by Z2 is a complex number lying somewhere on this line. Z1 by Z2 lies on the perpendicular bisector of the line segment joining minus 1 comma 0 and 0 comma 0. That means real part of Z1 by Z2 for sure is minus half. So what is Z1 by Z2? It is minus half plus some a times iota. I don't know what this is. But I know that Z1 by Z2's distance from 0 plus 0 iota is 1. This means magnitude of Z1 by Z2 is 1. So it means square root of this square plus this square is 1, or I can say 1 by 4 plus a square is 1 square, which is 1. So a comes out to be, a square is 1 minus 1 by 4, which is 3 by 4. So a is plus minus root 3 by 2. If a is plus minus root 3 by 2, Z1 by Z2 is coming out to be minus 1 by 2 plus minus root 3 by 2 iota. 1 by 2 you take out common, you have minus 1 plus minus root 3 iota, which is nothing but omega and omega square. So Z1 by Z2 is coming out to be option number B and C, which is omega and omega square. Next question, let's see what is it. Modulus of complex number whose reciprocal is given by the first column is what? Match it with the complex numbers given in the second column. Let's do it. First complex number is 1 upon a plus 1 upon b plus iota c. If you take out the exact complex number, it is b plus iota c plus a. So it is a plus b plus iota c upon a into b plus iota c. This is my reciprocal complex number. So mod of this is mod of this, which is mod of the numerator upon mod of the denominator. Mod of the numerator is under root a plus b whole square plus c square, and denominator is mod a common, and then magnitude of b plus iota c, which is b square plus c square, is 1 by mod z. So mod z will be what? It is mod a into under root b square plus c square upon under root a plus b whole square plus c square. So mod z in this case turns out to be mod a times b square plus c square under root upon under root is a plus b whole square plus c square. So a gets matched to r. Clear? Then you have 1 upon a minus iota b minus 1 upon a minus iota c. Let's do that. It is a minus iota c minus a plus iota b upon a minus iota b into a minus iota c. Clear? A gets cancelled, you have iota common b minus c upon a minus iota b, a minus iota c. So magnitude will be what? Magnitude of this upon magnitude of this, right? Mod of iota is 1, so this just becomes mod of b minus c upon under root a square plus b square into under root a square plus c square. So you basically get mod z equals to reciprocal of this, which is under root a square plus b square into under root a square plus c square upon mod of b minus c. So b gets matched to p. After this, what is it that you have? Let's see. You have a minus iota c plus a minus iota b, right? So you basically have a minus iota c plus a minus iota b upon a minus iota b into a minus iota c. So you have what? A plus a is 2a minus or plus iota, or let me take it minus iota times b plus c. Why? Because it is minus iota b minus iota c whole upon a minus iota b, a minus iota c. When you take the mod, you basically get under root 4a square plus b plus c whole square whole upon under root a square plus b square into under root a square plus c square, right? So over here, if you try to understand from here, what I can do is, if you see r, yes, so r and q have already been taken. I am left with what? This is p. So r and p have already been taken. I am left with q and s. If you try to understand what is this particular point trying to say, it is a small correction. Here it will be b upon a plus iota b plus c upon a minus iota c. Now if you try to decode the correct option, what would that become? It will be 1 by z means ab minus iota bc plus ac plus iota bc whole upon a plus iota b into a minus iota c. This gets cancelled, you are left with a times b plus c upon a plus iota b into a minus iota c. This is 1 by z. So the magnitude will be magnitude of this upon magnitude of this, which will be what? Magnitude of a, magnitude of b plus c upon under root a square plus b square into under root a square plus c square. So if you see, S happens to be the correct option for this, so C gets matched to basically S. Last is 1 upon a plus iota b plus iota c. So 1 upon a plus iota times b plus c, this is very easy. This is 1 upon under root a square plus b plus c whole square. So your answer is under root a square plus b plus c whole square, which is q, so D gets matched to q. Moving on to the next, we have if the equations this and this have a common root, then which among these is the correct option? Okay, so alpha is suppose the common root, okay. So alpha will satisfy this and this, so you have alpha square plus b alpha plus c is 0, and you also have b alpha square plus c alpha plus 1 is 0. Just multiply this by b, the entire first equation by b. What do you get? So you initially had alpha square plus b alpha plus c is 0. You multiplied it by b throughout and then perform this subtraction. You basically get this getting cancelled. You have b square alpha minus c alpha. So it is b square minus c plus bc minus 1 equals 0. So alpha turns out to be 1 minus bc upon b square minus c. When you plug this value of alpha in here, you basically get 1 minus bc whole square upon b square minus c whole square, this is alpha square, plus b into alpha plus c is 0. Okay? Now next what you get is, once you have this being satisfied, when you eventually solve this out, you get 1 plus b plus c. After that you have bc plus b plus c, 1 plus b plus c, bc square plus b square plus c square, minus bc minus b minus c equals 0. Clear? Which you can write as what? Half of 1 plus b plus c into, you will have b minus c whole square plus b minus plus c minus 1 and b minus 1. This is 1. Okay? So you will have b minus c whole square plus b minus 1 plus c minus 1. That's what you're going to have. Okay? So here, when you get this on simplification, you can just modify it into this, and therefore this is going to imply that for this equation to be equal to 0, either this is 0 or this is 0, which eventually is going to give you your answer that either this is 0 or this is 0. So it is these conditions which are going to imply having these two quadratic equations to have a common root. Now when I move ahead with the next question, we have A, B, C are in GP. A, B, C are in GP, then the equations this and this have a common root. Then what happens? Okay, so A, B, C are in GP, so you have B square equals AC, or B is root AC. So this equation becomes what? This becomes AX square plus 2BX 2 root AC into X plus C equals 0. C you can write as root C whole square, A you can write as root A whole square. This becomes root AX plus root C whole square. So X turns out to be minus root C by root A with multiplicity 2. Because this is a common root, so it will satisfy the next equation also. So you have dx square, d and square of this, which is C by A, plus 2ex, 2ex, x is minus root C by root A, plus f equals 0. Send this to the right hand side, you have dc by A plus f equals 2e root C by root A. Divide throughout by C, you get d by A plus f by c plus 2e by, or this is equal to 2e by root AC. But root AC is b, so this becomes 2e by b. So you are getting twice of e by b is d by a plus f by c, which means d by a plus d by a, e by b and f by c are in AP. So you are getting d by a, e by b, f by c are